Hello everyone, I am Richard Wang, an 8th grade student. Today I will be presenting my project, Detecting Blood Cell Aggregation Disorders with Machine Learning, measuring blood cell properties in microfluidics device with a combined approach of machine learning and traditional computer vision method. I am grateful for Dr. Yang Xu of San Diego State University, who supervised me in this project. Introduction. There are many disorders associated with the clumping or clotting of blood cells. These include erythrocyte aggregation, coagulopathy, and red cell agglutination. Examination of erythrocyte velocity aggregate characteristics, in other words, observing the speed and clumping of these red blood cells, is critical in assessing such disorders. Note that my project focuses more on the clumping aspect. My project automates the process of detecting blood cell clumping. I wrote my project in Python, and for data I used flowing blood cells in microfluidics device containing dextrin. To detect blood cell clumping, I first needed to detect the blood cells themselves. For this I used two methods, computer vision algorithm and machine learning-based object detection. Then I combined the two and detected clumping very successfully. My first method was the half-circle algorithm based on the half-circle transform. It is a feature extraction algorithm built in OpenCV Python. It detects candidate circle centers, in this case of the blood cells, and then determines their best radius. Applying it on images, it was very simple to tune and use. However, the parameters were dependent on image context. My results were very successful. Most blood cells were detected. However, there are a few false positives. The noise can cause inaccuracy. Also, half circles cannot accurately detect the blurry cells at the centers of large clumps. My second method was to use machine learning-based object detection. Specifically, I used a model architecture known as faster RCNN. This is an object detection model, which means that you feed it an image, and it returns the positions of where it thinks things are. Faster RCNN stands for Faster Region-Based Convolutional Neural Network, and its complex architecture is shown here. Currently, there are some other projects similar to mine, such as the BCCD dataset, a small collection of annotated blood cell images that also uses object detection in faster RCNN. To train my model, I used my results from half circles as a dataset. This was suboptimal, as human-labeled data would be better, but this was unavailable. I trained on around 7,000 images, and used for my loss function GIOU, which stands for Generalized Intersection over Union. My results are also very successful. Most blood cells are detected, and the average GIOU loss is 0.85 out of 2. But there are some issues as well. False negatives in that some cells are missed, as can be clearly seen. This perhaps could be due to the stochastic nature of training, as my batch size was only 16, or the slow convergence of GIOU. There is also difficulty finding isolated or blurry cells. At this step I thought, what could improve the performance of both half circles and machine learning? Perhaps the answer lied in complementing algorithm and model, combining the two. The model could serve as a validation for the half-circle detections, not too few nor too many detections. After that, I implemented the dbScan algorithm from scikit-learn, which stands for Density-Based Spatial Clustering of Applications with Noise. It determines clusters in a list of points, based on each point's neighbors. I performed dbScan on the centers of the blood cell detections. My results are excellent. Every large clump is consistently detected, and the smaller clumps can also be detected. Zooming in on my results, the key is complicated, but the takeaway is that the yellow bounding boxes, representing the hybrid method of half circles and machine learning, are very good at detecting these blood cell clumps. Now, let's watch my pre-recorded video briefly explaining my code and results. This will be a brief explanation of my code and results. I have included the most important files of my project here. In this first file, I applied Huff circles onto many images and wrote my dataset. After that was training the faster RCNN model. Models.py defines some crucial classes and functions, including GIOU loss and detection pruning. Next, the excitement of training the model. After loading the data, I trained the model on these hyperparameters and then did testing on it. Okay, now both Huff circles and the model are complete. The last file combines algorithm and model, then uses dbScan to find clumping. Here are some of my results. This is the result from Huff circles, and of course it can be seen. It is quite nice. Most of the blood cells are detected very accurately. Next, here are 3 images showing the gradual improvement of my model. As can be seen, the last one is much better than the first, as I refined and fine-tuned the model. And this is the final clump detection, showing highly successful results. Now, back to my presentation. Okay, that is the end of the video. Let me now talk about the challenges I overcame. First and foremost was learning new tools and concepts. Libraries like NumPy and OpenCV, concepts like machine learning, and much more. At the beginning of my journey on this project, I was searching for an algorithm, a computer vision algorithm, that could detect blood cells very well. I settled upon Huff circles. Implementing it into the dataset proved to be a challenge. Even more difficult was training the model. To create the best model, I had to make considerations for the loss function and tune the hyperparameters, and rely on a bit of luck for the initializations. For future improvement and research, I would like a larger training batch size. Larger batch size could give more accurate convergence, but this is currently limited by the GPU server's memory allocation abilities. A more comprehensive training dataset would also be very good. It would, of course, be larger, and also there would be more variation in the training data, like brightness differences. This could make the model more robust and generalized. For future research, I might use a YOLO model. YOLO is an alternative object detection net that stands for You Only Look Once. It may or may not be better than the faster RCNN used this time. I also might consider trying DIOU or CIOU loss, cousins of GIOU standing for distance intersection over union and complete intersection over union respectively. And finally, this is something I'm starting to work on, is detecting blood cells from in-eye images, clump detection in vivo for patients. This has many similarities and differences to this project, but the methods I've used here should be able to be applied there successfully. Here are some of my references. Above are the GitHub links to my code, and below are many of the sources that helped me throughout this project. If you have any questions, please put them in the comment section of this video. But do not subscribe to this channel unless you are prepared to watch many unrelated videos. Thank you.